Before we start pre-processing, I'll take a minute to talk about the importance of balancing your dataset. Let's think about a photo classification problem with two classes, cats and dogs. What accuracy do you expect from a good model? Well, if we correctly classify 70% of the photos, that's not too bad. 80% accuracy is good, while 90% is very good for beginners, right? I'm not talking about Google and Facebook classifications, which achieve 99.99% accuracy. 90% accuracy for most problems is an impressive accomplishment. Okay, now imagine a model that takes animal photos and outputs only cats. No matter what you feed to the algorithm, it will always output cat as the answer. A bad model, isn't it? Is this machine learning, you may ask? It's definitely not the result we want from a machine learning algorithm, but is a common result. Imagine that in our data set, 90% of the photos are of cats and 10% dogs. The same awfully bad model applied to this data set would classify all photos as cats. But 90% of the photos in that data set are cats. What's the accuracy of the algorithm? It is 90%. Incredible! Why does this problem arise? Well, since the machine learning algorithm tries to optimize the loss, it quickly realizes that if so many targets are cats, the output should most likely be cats to achieve a great result. And therefore, it comes up with the same prediction at all times. Cats. Okay. Now, if the distribution of photos is 90% cats and 10% dogs, a model with an 80% accuracy is a bad model. Why? Because the dumb model that outputs only cats will do better than it. Therefore, only a result above 90% is a more favorable one. We refer to the initial probability of picking a photo of some class as a prior. The priors are 0.9 for cats and 0.1 for dogs. The priors are balanced when 50% of the photos are cats and 50% are dogs, or 0.5 and 0.5. Examples of unbalanced priors are 0.9 and 0.1, 0.7 and 0.3, 0.6 and 0.4, and so on. Each pair is prone to the issue discussed a minute ago. A machine learning algorithm may quickly learn that one class is much more common than the other, and decide always to output the value with the higher prior. Okay, if we have three classes, cats, dogs, and horses, balancing the dataset would imply picking a dataset where each class amounts to approximately 1/3 of the dataset. If we have four classes, 25% each. You get the gist. In our business case, by exploring the targets, we quickly realized most customers did not convert in the given time span. We must surely balance the dataset to proceed. That's done by counting the total number of target ones and matching the same number of zeros to them. All right, we'll do that in the next lecture. See you there!